Hey, welcome to another video. So in this video, we're going to talk about inequalities as they relate to polynomials, and the next video is inequalities as they relate to rational functions. But before we begin this, I really need you to have watched the last video when we talked about inequalities from a graphical perspective. I need you to understand what it means when a function is less than 0, when a function is greater than or equal to 0, and finding the interval on the x-axis which causes that. I need you to really grasp that. You see, what we're going to do here is we are going to think of these as functions. It is a function, but I need that mental picture to be in your head because I'm going to teach you two approaches. The first one is going to be graphically, just like we did in the last video. We're going to get a picture just like that. It makes it very, very nice. And then I'll teach you kind of a different way to go where you can just plug in some values and check the inequality to see whether it's true or false. So we're going to talk about that as we go. But again, you really got to watch that video. You got to get down this idea of a function relating to 0 and the x-intercept interval that we get from, the x-axis interval that we get from that. So let's take a look at it. If we consider this polynomial as a factored version of some function, oh man, do you see it? Do you see that this is a function? It's just asking where on the x-axis is this function less than 0. In the previous video, it's doing this. It's asking that question right there. On what interval of the x-axis is this function giving you negative outputs? Not even x-intercepts, just strictly negative outputs, or the graph will be below the x-axis, not even equal to it. So what that's going to do is ask you to do the following things, and basically all of this stuff. Firstly, find x-intercepts. That's really nice when it's factored already. Identify what those x-intercepts are. Are they crossings? Are they bouncings? And then get a mental picture of that. If we can do that, it's really easy to identify where the graph is below that x-axis, and that's what this is asking you to do. So if we don't just fall into the zone of this is an inequality, I do this and this. If we fall into the zone of, hey, that's a function, and you guys are so smart at it, you guys know that you've been watching videos hanging with me here, it's going to be easy. So we just understand that's a function. It's asking where's the function less than 0. No problem. Identify your x-intercepts. Why? Well, x-intercepts are where the graph has the opportunity to cross or bounce, to be above and then below, or below, above and above, or vice versa. We can go below and above. It can cross or can bounce there. Those are the opportunities where the function has to change from above to below. It creates the kind of the boundaries of our intervals. And so we ask the question, if this function is below 0 on part of the x-axis, let's find out where that is. X-intercepts are a big part of that because they're where you can cross or not cross, bounce. So we say, all right, let's do the same thing we've been doing for a while. One x-intercept would occur at 5, and another, because this is factored by the zero product property, would occur at -2. So we're going to put that on that number line. Remember, a number line like this is just the x-axis. But we're also going to put a little bit more about this. We're going to do two extra things when we think about this graphically. This is going to do two things for you. Number one, it's going to help you really solidify graphing in your head. And number two, it's going to give you a very, very, very nice picture of what's going on so you don't make mistakes. We're going to put down what these x-intercepts actually are. Are they bounces? Are they crosses? So this came from this factor, which has a multiplicity 2. We should know right now that that creates a bounce for us. Or a touch, we sometimes call it. This factor has a power 1, which means that we are going to have a cross here. If we can just get our end behavior, oh man, do you remember your end behavior? End behavior says we would get an x to the second power times an x to the first power if we distributed. That's x to the third. That's an odd. So here's how this has to look. We don't have to be super accurate about it, but here's how this has to look. We have a cross and a bounce. This must look like this. Odd says we start here, we end here. Remember, odds look like that, or something along those lines. So if our odd has to look like this, because it's a positive odd, we have to start here. We've got to cross, come back down, bounce. That models our odd, that models our cross, that models our bounce. And now we get a very, very clear picture of where this function is below 0, below the x-axis. It's just like the last video, only we're doing the graph now. So that's why that video is there. That's why a lot of textbooks introduce inequalities with those graphs, but a lot of times that connection is not made. We can do the same graph. And so we just think about it. Okay, hey, where is this, on what portion of the x-axis is my graph below the x? From negative infinity to negative 2, no problem. Not including the negative 2 because that is an x-intercept, but we're not including x-intercepts here. We want strictly negative outputs. Above, 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 oh, and then continues to be above, above, above. No problem. This is only one interval from negative infinity to negative 2 where this function is below the x-axis. I'm going to change this slightly, just a minute, and I need you to see it. What if this had been equal? If that had been equal, hopefully in your head right now you'd say, yeah, you know what, if that was less than or equal, it would include all the negative outputs, but it would also include the x-intercept. That would include that negative 2. But it would also include one other point, and I need you to see it. I need you to see that this would be below, 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 equal, above, 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 and equal. It would include a single solitary value of x that would allow this function to be on the x-axis, and that would be at x equals 5. How we show that? We put a union and we put the individual value of x that's allowing this function to equal x, and that's what we're equal to 0, which is on the x-axis. So we're allowing that, and you put a curly bracket. That's how we show an individual value of x that's causing this to be true. And that's it. So we see that in the next example, which I want you to try on your own, actually, after we factor it together. And then we'll kind of understand how to deal with that. So this is really about all there is to it. What we're going to be doing is we're going to think of this as a function as above or below the x-axis or on the x-axis. Draw a very, very quick picture of it, and then just consider what it's asking you to do. There is another way to do this. I'm going to show it to you right now before we move on to the next example. The other way that we can do this is we can sort of test values and see if they're true or false in our original inequality. Honestly, I think that takes a little bit more time because you're very good at graphing. You understand this stuff, which makes it quick. Plugging in values can be a little slow, but there are some shortcuts which I can show you. The one thing that I do need to make sure that you understand is that with quadratic inequalities, you always got an alternating truth. It was always true, false, true, or false, true, false. For if you had two x-intercepts, it was always that case. That does not happen anymore. Because we have this whole bounce idea, what happens is we can have the same truth statement. We're going to talk about that right now, and then we'll go on to the next example. So here's the idea. If you want to test values rather than graph, it's perfectly acceptable. Any instructor I know would accept that. Just be very careful with it. Here's what testing values would do for you. So we'd say, hey, you know what? I'm going to test a value in each of these intervals and see if it's just true or false according to my original inequality. So remember, we've got that. I'm going to erase that. I'm actually going to erase our graph for a second. So we would evaluate numbers like 6, that's somewhere in this interval, 0, that's somewhere in this interval, and maybe like -3, that's somewhere in this interval. And we'd evaluate that in our original inequality right here in the function. So we take a number like 6 and say, okay, if I evaluate 6, I'm going to get 6 minus 5, that's 1. 1 squared is 1 times 8. 6 plus 2 is 8. 1 times 8 is positive 8. It is not less than 0. Well, that's a false statement. And what that means is that every single input in here is going to give something that is a false statement according to our inequality. Something that's positive, actually. And so we're just going to put a big fat F. I'm also going to show you how to cheat at this in just a second. If you evaluate for 0, okay, 0. 0 minus 5 is -5. -5 squared is 25. All right, 0 plus 2 is let's see, 25 times 2 is, I really don't care about what it is, but it's positive. It's positive 50. That means, I think it is. Yeah, it looks like it. Positive 50 is not less than 0. So this is also another interval for which every single input is giving you a positive output and not something less than 0. How do we know every input in there does that? How do we know that? These are the only two x-intercepts that exist. Otherwise, it'd be factor different. Those are the only two that exist. And because polynomials are continuous, they don't have any asymptotes, they don't have any holes in them. Well, you have to be all above here because there's no way to drop below the x-axis on a polynomial without crossing it. You can't do it. Now, with rational functions, you can because of the whole vertical asymptote idea. But those will be on our x-axis, and so we'll be able to see that. And I'm going to give you some tools for how to find that as well. So we go, all right, well, I know every input here has to give me a positive output. Well, those aren't below 0, so this is false. And lastly, we plug in -3. That's going to be -8 squared 64 times -1. Well, that's -64. And so -64 is for sure less than 0. Oh, well, that means that's true. That means that every single input in this interval is giving me a true statement or something negative. And so once we've outlined whether our intervals are causing something that's true for an inequality or false, we just take the true segments and we say, hey, the only true interval here that works in my inequality is -infinity to -2. One drawback is that I've seen just a ton of students accidentally make their interval to -3, the value you plug in. That's not what's happening. This whole graph will be below the x-axis from -infinity to -2. That was just your testing point, your testing value to represent every input on that interval. So we'd say -infinity to -2, not including the -2, because we're not really caring about those x-intercepts. And that's exact, well, we had it first. Like that. Like that. So we're saying we want everything that gives negative inputs, not including that 0, not x-intercepts. So the way to cheat at it, this is kind of cool. You do the same exact thing. You do x-intercepts, bouncies, crossies, you write them down, and here's the deal. Because of the way that graphs interact with a bounce or with a cross, you can sort of cheat at this. Plug in the easiest number that you can think of. Plug in 0. If you can't plug in 0, plug in something next to 0. Plug in something as easy as you can. So we plug in 0 and we go, okay, if I plug in 0, I get something that is false. We've already done it. And then think. Think about what bounce means. Think about what cross means. Bounce means that you come down and you have the same output sign as you had before you bounced. So if you were positive, you remain positive. If you were negative, you remain negative. What that means is that if this interval is false, then if you bounce, you're still going to get a false. Keep the same truth statement on both sides of your bounce. False, false, or true, true. That will always be the case for you on a bouncing x-intercept. Hopefully that makes sense to you. Bounce maintains the same sign. And so if one's false, the other's false. If one's true, the other's true. Crosses don't. Crosses change sign. So if crosses change sign, then one of your intervals would be true and the other false. One would be positive, one would be negative. Or one would be positive, one would be negative like this. But somehow that's how crosses work for our x-intercepts, is we change from a positive to a negative or a negative to a positive. So if this is false, then this will be true. Your truth should change on opposite sides of a crossing x-intercept. Same for bounces, different for crosses. So if I were to do this really quickly, honestly, I'd probably graph it because that's quick. But if I had to plug in a value, I'd plug in something really easy, figure out whether it's true or false, and then what I would do is identify bounces, crosses, same truth for bounces, opposite truth for crosses. That's all you really got to do. The other one thing I would tell you though is this is a great way to check your work, to understand that bounce has the same truth and cross has opposite. That's a great way to check your work, even if you do the graphing. That's all I really want to say about it. What you should do now is pause the video and try that example on your own. Factor it first and then see what you get. So of course we're going to get to it now. If we factor this and we think about this as the question, where is my function greater than or equal to 0? Or in other words, on what portion of the x-axis is my graph above the x, or positive outputs, or equal to the x? X-intercepts. That's all we're talking about. So how that starts is find your x-intercepts. That means we got to factor. That also means we're identifying the x-intercepts. We're also going to say what they are, whether they're cross or bounce at those x-intercepts. Why? Because we know that relates to our truth, that relates to our graph. So we have said this is asking whether the function's above the x-axis or on it. We found the x-intercepts because that signifies where a graph is above or below. That separates our boundaries, sort of, where a graph is above or below the x-axis. Now we're saying because this factor had an even power and even multiplicity, that's a bounce. Because this factor had an odd power, that's a cross. Due to our multiplicity, let's put them in order on our x-axis on the number line. We know that's a bounce, we know that's a cross. I'm going to show you the second technique I showed you on this example first here, just so you get that I'm not trying to sway you on which one to do. I really don't care. What I would do on this problem if I was not going to graph it is I would think, hey, what's the easiest number I can think of to plug in and where does that fit? I can think of to plug in like 1. If I plug in 1, that's pretty easy here. You can do it anywhere you really want. And I'm just going to see whether that's true or false. So if I plug in 1, let's see, 1 cubed is 1. Minus 4 times 1, 1 minus 4, that's negative 3. Is negative 3 greater than 0? No, that's false. So what that signifies is that everywhere between 0 and 4, as that's the representation, a representative of those inputs, it's going to give me something that's negative, less than 0. That's not what we're looking for. So this interval is all inputs that are giving me something that's not true for my inequality. Now let's be smart about it. If that's false and this bounces, this interval is also false. A bounce does this and this, or this and this. It doesn't really matter how it's going if you're going to use this technique. All that really matters is this interval is false, this was a bounce, so that interval is also false. They have to have the same sign on opposite sides of a bounce. If that's false and this is a cross, that's true. You have to have opposite signs on different sides of a cross. So if this interval is false, this one has to have the opposite sign and is therefore true. So it appears the only true interval is from 4 to positive infinity because that's this number line, that's the x-axis. We have to be very, very careful though. Oh, and I hope that you see it. I really do. This is also asking you for function values that are equal to 0, function values that are on the x-axis. Those are x-intercepts. So when you do this and you identify that's an x-intercept, so is that one. This equal is including those x-intercepts, even the 0. So even though that's false and false, it's bouncing here, isn't it? So somehow it's bouncing there. That means it's on the x-axis. That's allowed. That's something we collect and keep with this. Therefore, we have to include that 0 as well. That is an x-intercept, and that's included in being above or on the x-axis. Outputs that are positive or 0 includes x-intercepts, and that's one of them, so we have to include that. I hope that makes sense to you. Now, the graphical approach to it. If we did this a little bit differently and said, hey, there's a bounce, there's a cross, I do the same exact thing here, I write everything exactly the same, I know that my leading term is x cubed. X cubed has an end behavior that looks like that. So what this says is, if my end behavior is a standard cubic, it's going to come up. This is bounce, go down somehow, come back up and cross at x equals 4, and then we can actually get a better picture of it. Where is my function above or on the x-axis? above on this interval, on here, and here. And that's exactly the same interval notation that we would get. So I hope that's making sense. In just a minute, we're going to do 2 more. You should be fairly decent with it at this point. What I'm going to do is put them on the board and ask you to kind of pause the video and do them on your own, and then I'm going to go right through it. All right, we're going to get to it. So there's just 2 more. Again, pause this video and try these. The one thing you need to know before you pause it, hopefully you haven't paused the video already. One thing you need to know before you pause it is, while this is a cubic and asking where it's greater than a line, it looks like this. Where is this cubic above this line? Here and here. And according to the x-axis, it's asking on what portion, this is the English part of it, on what portion of the x-axis are the inputs making these outputs more than these outputs or equal to it, where they intersect or where this cubic is above that linear. That's what it's looking like. This is a picture of that, but this is very hard to do the way that it's written like that. We'd have to do a lot of other things that are much harder than doing a very simple manipulation. So the simple manipulation is what this problem translates to, where a cubic has outputs greater than a linear, or again, the translation is where are the inputs giving you outputs here that are more than this? Where's the function above the line? Where's the cubic above the line? That translates to this. If you get everything on one side in order, first term positive, and 0 on the other side, that translates to a different question with the same interval of the x-axis. And that's the way we get away with this. Remember that what this question is asking you isn't, it's asking you where is the interval that causes this function to be more than this one, or where's the interval of inputs where this function is more than 0. It's a slightly different question. It translates this graph into this graph. So where this function is above the line is where a different function is above the x-axis. Different look, but the same interval of the x-axis. That's kind of neat. Making a little shift in our idea that changes the look of our picture, but getting the same interval of inputs that causing both of these to be true. They will have the same solution set. Both of them are asking the same question in a slightly different way. One saying, what's the set of inputs that makes this output greater than this one? This one's saying, what's the interval of inputs in making this output greater than 0? It's going to be the same interval. So set everything on one side greater than or equal to 0, or just manipulate, so you have 0 on one side of your inequality. And now what I want you to do is factor completely, find your x-intercepts, and see if you can determine what our true and false intervals are. So we're going to do that right now. The first thing we've got to do is factor and find our x-intercepts, because that's where we change from above to below 0. Our signs can change there. So we factor out our GCF of x. And then this factors is pretty nice. This is x plus 3 and x minus 1. And we have 3 x-intercepts. We've got x equals 0. X equals negative 3. And x equals 1. So we set our factors equal to 0. We solve them, not too bad. We got 0, we got negative 3, we got positive 1. All of them are crosses. So that's a power 1, power 1, power 1. All of them are crosses. All we got to do is put them in order. Understand a bit about our end behavior, and then go for it. So our end behavior is a cubic function. Right here, this is really what we're doing. This is the x-axis. This is your cubic, and we're asking what are the intervals that's causing the outputs of my function to be greater than 0? Or in other words, where's the function above the x-axis or on it? If we know it's a cubic, then this has to have this odd end behavior. We know that. So we're going to be down here, cross, 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 and up here. Oh, that makes sense. That's a picture of my graphing. Hopefully you can tell why I like this technique for you guys, because it's really going to kind of solidify the graphing in your head as you go through it. That's the one way to accomplish this, and just do the intervals where the graph's above and equal to the x-axis. The other way would be to plug in a value. I'd probably plug in 2. 2 seems like it's going to be the easiest one to plug in for me. So here's the second technique, and I'll show you the graphing technique. If I were to evaluate 2, so evaluating 2, plug in 2 here, or plug it in here, because that has the 0 on it. That's what we need to know. So plug in 2, and we go, all right, probably here would be okay. 2 times 5 times 1. Plug it in 2, not 1, it's going to give a 0. We'll plug in 2. 2, 5, and 1. That's going to give us 10. Is 10 greater than 0? Yes, that's great. So that says that every input from 1 to infinity is going to give us a positive output, and that's exactly what we are asking for. So true. How about this one? Opposite truths across from crosses. Opposite truths on different sides of crosses. So this is a false, and then another cross, true, another cross, false. Guaranteed the truth is going to look like that. So there are 2 working intervals here. One is from -3 to 0. The other one is from 1 to infinity. We never include infinities. You got to give me a parentheses, but we are going to include these values because we know they're x-intercepts. That's why we put crosses here. We know they're x-intercepts, and we're asking for x-intercepts. So we're going to include those. That is the solution set. That's the interval for which this cubic is above the x-axis, and also where this cubic is above that linear. That's interesting. Same interval, same inputs, and that's all we're looking for. What are the inputs that cause this to be true? What are the inputs that cause these outputs to be above or equal to those outputs? There they are. They're right there. Graphically, similar, but done a little bit different. So we're going to get the same truth, but you're going to get a picture of it rather than just the true, false, true. Which one's better? Whichever one makes sense to you. Whichever one you think is easier. Because we understand the end behavior and we understand the crosses here, we can say where we are above 0, above the x-axis or on it, is from -3 to 0, including that because those are x-intercepts, and then from 1 to infinity, including the 1 because that's, again, an x-intercept. We get the same exact solution. Okay, last one. Seemingly simple sort of problem. Let's think about what this means. What this is asking you is, where is this power 4 function greater than 1? Well, this is the x-axis, so really the picture of it is, here's x equals 1, or sorry, y equals 1. Where is this power 4 above it? That's really all it's saying. On what portion of the x-axis is my degree 4 x to the 4th power greater than 1? So above this horizontal line of y equals 1. We can translate that, and it's a literal transformation. Check this out. If we subtract 1, that changes this question to, where is x to the 4th minus 1 greater than 0? Now, why does that work? This is a really nice one for us to see. If you take x to the 4th power and subtract 1 from it, what's that do? Wow, we got to be thinking that's a vertical shift, right? So that's the same question as if I took this whole thing and shifted it down 1 unit, everything would shift. The same exact graph is answering the question for where this function is greater than 0 is where the non-shifted function is greater than 1. It's the same thing. You would just take this, shift it down, you get the same interval on the x-axis. I kind of missed it there. but it would answer the same exact interval. And so we're going to show it this way because this is easy to factor and this one's really hard to kind of do algebraically. So we're going to factor this. We're going to put our x-intercepts on the x-axis. We'll figure out where we're above that x-axis and that will answer this interval for us. So the factored version of this, it's got a difference of squares and it's got it twice. So we can factor as x squared minus 1 and x squared plus 1. We can't factor x squared plus any other number. It's not possible to do. It's called an irreducible quadratic across the real number system. And since that's what we're dealing with, we can't factor anymore. But this difference of squares, we can. So what do you do with this one? You actually do nothing. It's not going to do anything for you as far as x-intercepts. Because you can't solve it in the real number system, it can't cross the x-axis, or it's not creating any additional crossings. These two do, though. Since we know that we're going to cross, hey, that's a power 1, that's a power 1, that's multiplicity 1, that's odd, that means that we're crossing those x-intercepts. There's only two of them. So we have a cross and we have a cross. Hopefully we understand that if this is a power 4, this is just that power 4 power function and even shifted down 1 unit. It is going to cross the x-axis. That's what's happening here. It's crossing those two locations. We also should understand that if that's a power 4, it's got end behavior. If we have crossings, it's going to look something like that. It has to cross and then cross. It actually has symmetry on it, so it shouldn't come as a surprise that our truth has to be the same here and here. It does have that symmetry. We also know that truth should alternate here. Oh man, that should be just right in your head, that this should alternate. Should be true, false, true, or false, true, false, depending on what we're asking here. And since we're asking where is this function greater than 0, where is it greater than 0? That's greater than 0 from negative infinity to negative 1, and then again from 1 to infinity. Do we use brackets or parentheses? Well, since we don't have the equal sign, we are not asking for x-intercepts. We're asking for strictly what inputs are giving positive outputs. Where's the graph above the x, not equal to it? That's negative infinity to negative 1. And then from 1 to infinity. Those are the two intervals that cause these outputs to be positive or above the x-axis. That's where this graph is going to be above 0. That's where this graph is going to be above 1. If you unshift it, the same interval works. It's kind of neat. If you wanted to plug in a value, of course we could plug in 0. 0 is really nice. 0 to the 4th power, 0 minus 1, well that's negative 1. Is negative 1 greater than 0? No, it's not. Crossings say that you have opposite truth, and we get the same intervals. Negative infinity to negative 1, 1 to infinity, but use parentheses because we're not asking for x-intercepts. Here's what I hope. I hope, number one, it's made sense. I hope I've made a connection between graphing and these inequalities that we're doing. That's what I intended to do. Sometimes we treat inequalities. If I had just taught you to plug in a value, we would not be seeing the connection of the graphs with this. And I want you to see that. I want you to have that knowledge because it's there, like it's right there. It will really help you with this idea if you understand the crossing versus bouncing and why those truths have to be different. Well, that's important. That's why we study multiplicity and all that, and now put it in conjunction with these inequalities. So I hope I've made sense for you. Really get this stuff, because in the next video, we're going to deal with inequalities with rationals, and we play a lot of these same concepts. So I'll see you for that video, and I hope you're all doing good.